No, class. Okay, so we're going to talk about energy in electric fields. So to start out, we're going to review the idea of work in physics. And so work is a combination of force and displacement. And we can let's start by just considering a simple case where we have a constant force. So again, work is a combination of force and displacement. So like say I apply a force to this object and it does not move, then there's no work being done on it. But let's say I apply a force to the right, and let's say it moves in the same direction. In that case, the work would simply be force times displacement. So this is a special case where the force and displacement vectors are parallel. Then the work done, it's a scalar, it would just be the magnitude of the force times the magnitude of the displacement. Now, another example of work, where we'll leave this displacement. Let's say the object is always going to have this displacement to the right. What if we look at the force, a force that is in the opposite direction of the displacement? Well, in that case, work would be, it's the same product of the force times the displacement, except now the work is negative. And again, this example, say you have an object sliding across the ground, friction is going to be in the opposite direction. And one final case we need to consider, what if the force is perpendicular to the displacement? So again, if this is an object sliding across the ground, that first force we could have said is an applied force, like we're pushing the object across the ground. That second one we described could be friction. This one could be a normal force or gravity. They're both perpendicular. And in this case, work would be 0. And so really that's all we need. Let's actually combine them and write them all down at once. So this is F1, this is F2, and this is F3. So work 1, that's the work done by force 1. That'd be F1 delta x. The work done by force 2 would be minus F delta x. And the work done by force 3 is 0. And again, this is really all we need for our definition of work. Now, again, we didn't really consider the most general case. What if we have, say, a force that's at an angle? So F4 is at an angle. And again, this is really nothing new, though. This is enough for a definition of work. Because if you have F4, you can always break it up into a component. Move this down a little. Let's call this Fx. And that one Fy. You can always, because our displacement is in the x direction. So if we have a force that's at an angle, it's not, in the direction or perpendicular, we can break it into a parallel and a perpendicular component. And so the work due to F4, well, that'd be the work, this would be Fx times delta x. So that'd be the work due to this force, plus the work due to the y component, which is 0, because this force is perpendicular. And so, this work done to work done by F4, that's nothing new. We already knew how to handle that. So we can make this much more compact, though. Just in general, say the work is equal to F dot delta x. So that's the vector, we've got force and displacement, both vectors. And so we take the dot product, also known as the scalar product, work is a scalar. And that'll give us all three of these cases we talked about. Like in case 1, the angle, we can also write this as F delta x cosine theta. So in case 1, theta would be 0. They're parallel to each other. And so cosine of 0 is 1. We just get F delta x. In case of F2, they're pointing in opposite directions. The angle is 180 degrees. Cosine of 180 is negative 1. So we get that minus sign. For F3, the angle is 90 degrees. So the cosine of 90 is 0. And for F4, Fx would be F4 cosine of theta. Like if this is the angle between the force and the displacement. F dot delta x, that would give us F4 times delta x times the cosine of the angle. And so we get the same result. It's a more compact way of writing it. However, a little bit more, this is fine as long as we're dealing with, say, a constant force or a nice reasonable displacement. But what if we have a more complicated case? Let's say the force is variable. So say we have a variable force, and say our displacement is some path that we can't really describe as just a vector connecting the starting and the ending points. So we can't describe our displacement as a simple vector if it follows this path, especially if it's a curvy path. And so in this case, what we would do is just break our path into little pieces. And if we break it up into smaller pieces, each of these pieces is going to be approximately a straight line segment. So no matter how, any reasonable path, no matter how curvy it is, unless you have like a right angle, which we could also deal with, if you break up into smaller pieces, the curvature is going to be less significant, so we can approximate them as line segments, and then just use our definition for each line segment, and then add them all up. So our most general definition for work so again, we're going from, say, point A to point B, and ds would be like this this displacement vector, this infinitesimal displacement vector. And so again, that's our general definition of work. This is a line integral. Okay, so now let's apply this to the electric forces. And let's start out by considering a kind of a simple case. Let's say we have a charge Q1, which is fixed. So Q1 is not going to move, but it creates an electric field around it. And so let's say we have Q2 which starts at point A, and it's going to move to point B. Let's just say over here, I'm going to draw a nice straight displacement from A to B. And I'll draw a radial line here as well. And so we want to calculate the work done from A to B along this line segment. And we're going to do this in a particular way. let's say instead of following our actual path, so remember, we're going to break this path up into pieces, but now for the sake of the drawing, this ds vector is, of course, very small. We take the limit that it goes to 0, but I'm going to exaggerate these ds vectors just for the sake of the drawing here. So let's say instead of going directly from A to B, let's say we take a path in the purely radial direction. So let's call this ds1. And then ds2 is going to be this arc here. So we start out moving radially towards charge 1. But that'll take us off the path we want to be on. So we just go a little bit in this direction and then take this curved path back to get back on our target. And then we're going to repeat this again. So here, let's just call this path 1 and path 2. So now that we're at path 2, I'm going to draw another radial line to this point. And let's repeat this. We go in the radial direction for a ways, and then we cut back to get back on our actual path. Let's do one more. Now, of course, in reality, we'd want to break this up and do a lot more pieces. But you get the idea. We take this we go a little bit in the direction of the charge and then back to get on the path. And then do that again, except instead of doing it 3 times, we do it, 100 times or something like that. And then we add up the work over all of these paths. Now, again, we didn't exactly follow the path we were supposed to. However, imagine that these distances we traveled in the direction, in these radial directions, say these were a lot smaller. So maybe instead of, here's our actual path, we do this. I mean, it's kind of hard to draw, but we always, go a little bit in the radial direction. And you can see this looks a lot better than this one as far as sticking to the path. And again, if we make these increments smaller, we'll approximate the path better. And in the limit, we take the limit that each of these paths go to 0. Then the difference between this kind of wavy path that we're taking and the actual path is completely insignificant. And that can greatly simplify our calculation. So let's just look at paths 1 and 2. So 1 is this radial path. And then we take this curved path to get back on track. So let's look at the work along path 1. It's an incremental amount of work, so I'm going to call it dW1. And that would be just F dot ds. And another reason we have to break this path up into pieces is because the force depends on the distance. So let me draw the electric field. Let's do it in pieces. So we have F equals QE, and the magnitude of E is KEQ over R squared. And so again, just like calculating the work over some finite path, that doesn't really make sense because the radius is going to be different at the starting and ending point. So what would we plug in for R? But again, if you make the path small enough, then R won't change significantly over it. And again, once we do an integral, the result becomes exact. So again, that's another reason we have to consider these small increments in order to calculate the work. But here, force is Q times E. Forgot the dot here. And again, the electric field that's causing this force is E1, the electric field due to charge 1. Now, this dot product is going to be very easy now. So again, I said assume Q1 and Q2 are positive. Then the force is going to be radially away from radially away from Q1, where the displacement is exactly opposite that. And so we're going to pick up a minus sign here. We have Q2, or let's say minus Q2. So the E1 dot ds1 is minus E1 ds1. And then we're just going to integrate this, or let's kind of stop here. And so then for dw2, the work along path 2, that's going to be 0. Because path 2, we drew this as like a circular arc. And so like every point on path 2 is the same distance from Q1. And so the motion is always going to be perpendicular to the force. And so, dot product in that case is 0. So again, this going from this point here to this point here, again, the only work that was done was a work along this radial direction. This motion perpendicular to that is irrelevant. And so we can say in general that the work only depends on like how much closer or farther away you're getting from this charge. And so that's a very important property of electric fields. And what that means is that the work done by the electric force is independent of path. So again, say you have this going from A to B, like in a straight line. Let me redraw that picture. So we have Q1 and Q2. Again, that's point A. We end up over here. And say this is the actual path that the charge takes from point A to point B. Well, we could replace it with this one. That goes, just in the radial direction from, so let's say that this is R2. Like the point B is a distance R2, or actually maybe better, let's call that RB. So it started out a distance RA, ended up a distance RB. Yeah, we can calculate going from here to here so that this distance is RB. And then we end up at point B, but again, the work done over this segment is 0. So the work done along this path is the same as this combination. Now, if we look at a more general path, I'll try to draw this, but say we have Q1. And let's say point A is here and B is here, and we have some path that looks like this. So that's the actual path. So again, we can break this up into pieces, and let's, I'm going to try and make this a little bit easier to draw. Let's say A is here and B is here. So again, this is the radial direction. So it looks like we can start out just going on the radial direction, and then we get off path a little bit and just cut back. And then we don't really have far to go in the radial direction before we have to kind of cut over again. And then again, barely any direct, like very small increment in the radial direction. But now we're getting back where we'd yeah, just kind of, you know, like any actual path, we can approximate it by, you know, just these radial components and then this arc that is, you know, always perpendicular to the force. So like the electric force is outward. So like every point on this path is perpendicular to the force. And again, by making these increments smaller, we can approximate this path any way we like, as closely as we want, provided that we break it up into enough pieces. And of course, we're dealing with an integral here. We break it up into an infinite number of pieces. And so for electrostatic forces, the work done is independent of the path. And when that happens, we say that the force is conservative. So that is an essential property of electrostatic forces. So I'll just write it down here and we'll leave it. Now, why does that matter? Well, there's kind of two reasons why that matters. One is it can make calculations a lot easier. Like if you want to calculate the work along some crazy path like this, you'd have your work cut out for you. You'd have to break it up. You'd have to know the mathematical shape of that and do a line integral. But again, if I gave you a problem like this, you just say no problem. Just do a different and more convenient path like this. Because the electrostatic force is conservative, you can pick any path connecting points A and B. And so that can make your life a lot easier. Yeah, I mean, you just have a radial component. That's easy to calculate. We'll do that in a minute. And then this component, the work is 0. So, yeah, you're done then. But the real reason why it's so important is because the force is conservative and the work is independent of path, that allows us to define a potential energy function. So our potential energy function, it's a function of position. And I'll write down the definition. Like how we define potential energy. So we use U for the letter U for potential energy. And we can't really define potential energy as just a function of position. It's not quite that simple. Because potential energy is defined by work. And work has to follow some path. And so we can only define differences in potential energy. And so really, oh, sorry, this is wrong anyways. We have a minus sign. So UB minus UA, that's the change in potential energy. So we start at point A, we end up at point B. So the change in potential energy is UB minus UA. And that's equal to minus the work done. And hopefully you can see why this definition is only possible if the force is conservative. And I think the easiest way to see that is let's consider a non-conservative force. So a classic example of a non-conservative force is friction. So let's say we tried to define a potential energy for friction. So let's say this is our XY plane. So like say we're looking down on this object. Let's say I tell you an object starts at the origin. That's point A. And it's going to end up at point B, which has coordinates, say, 4 meters, 3 meters. Now the work done by friction, let's just look at the magnitude of work done by friction. That would be the force of friction, which, we don't need a number here, times the displacement. And so, if I ask you, so an object starts at A and it ends at B, how much work does friction do as the particle moves from A to B? And you can't really answer that question. Because let's say you go directly from A to B. Then the displacement is 5 meters. So the work along this direct path from A to B, let's say the force of friction is 100 newtons, just to make life a little easier. Then the work along, say, path 1, it's negative because friction does negative work. Whatever direction of displacement is, friction's opposing that. So we'd have the force, which is 100 newtons times the displacement. So this would be minus 500 joules of work. Now let's consider path 2, which will start and end at the same place. But say we push the object in the x direction and then push it in the y direction. The total distance traveled is 7 meters. So the work along path 2, these are both path 2, that'd be minus 700 joules. So we get a different answer. So if I ask you, what is the work done by friction connecting points A and B? You can't give me an answer. There's no way we can define a function where, in terms of friction, that would only depend on the endpoints, because friction is not conservative. But if it is a conservative force, we're guaranteed to get the same answer no matter what path we take. And we've shown that electrostatic forces are conservative. So when it comes to calculating the work done by friction, we can consider any path we want. And again, let's draw the picture again. We have Q1, Q2, Q1, and Q2 is going to start at point A, and it's going to end up at point B. And again, the most convenient path that we could take would be like this. So we go purely in the radial direction until we get the right distance from Q1. So again, this distance here would be RB, and then we go along this tangent path. So like at the radial direction, the force is always radial. And so like the displacement at each point is perpendicular to the force. So that path is always going to be perpendicular to the force at every point. And so the work done along that path is 0. And so if we want to calculate the work connecting points A and B, we can just calculate this direct line. That's it. So let's actually do that. So the work is going to be the force. Well, we've got the integral. We can take Q2 out. And again, we're going from point A to point B. And now let's put in our definition of the electric field. Well, first notice that E dot ds. Again, let's say Q1 and Q2 are both positive or both negative, so that the force is pointing away from Q1, then E dot ds is going to be negative. So we'll have minus, I took Q1 out as well, and we're going to have KE. Sorry, let me start over. We've got Q2. Let's just do one thing at a time. So the electric field is Ke Q1 over R squared. And then we take the dot product with ds. We pick up a minus sign. And so we can take this KEQ1 out. Now ds is, in this direction. However, let's convert this to an integral over dr. So again, we're still going from point A to point B. So yeah, this displacement is always towards Q1, where the r vector, or dr, is always radially outwards. So let's take these constants out. So we have Ke Q1 Q2, and we're going to replace ds with dr. So that'll cancel out that minus sign. And we're integrating from RA to RB. And this integral is trivial. It's r to the negative 1 over negative 1. So we have minus 1 over r from RA to RB. So this is going to be so we have minus 1 over RB, so let's write it here. And then minus 1 over RA, so that term's going to be positive. Let's put that in front. So this is the work connecting points A and point B. Ke Q1 Q2 times this thing in parentheses. I'm going to write this a little better. Okay, but now remember, work is equal to minus the change in potential energy. And so UB minus UA is going to be minus the work. So what we're going to do, the change in potential energy is going to be minus this. So let's flip these two fractions. If we distribute that minus sign into here, that'll make 1 over R negative and 1 over RB positive. So I'm going to erase this. And let's erase all of this. And let's write our final result. UB minus UA. So again, that's minus the work. Here, this is WAB, work from A to B. So again, we'll distribute the minus sign in the parentheses. So we're going to have KE Q1 Q2 times 1 over RB minus 1 over RA. And I actually want to distribute this. Say this is our final form for the change in potential energy moving from A to B. Okay. Now, the other conservative force, well, there's a couple other conservative forces you dealt with in mechanics. There was gravity, of course, and the spring force is also conservative. But let's look at gravity for a moment. That's probably the easiest one to deal with, particularly if we deal with gravity on, like, near the surface of the Earth. So if our force of gravity is just mg, it's a constant, then you might remember the potential energy in a gravitational field is mgh. And so, here we're describing the potential energy as if it's just like a function of position. Where here we have like a difference between 2 points. Here we have a change in potential energy. You might remember gravity, we just say the potential energy is given by this formula. There's a big difference between these two cases. Now, how do we do this with gravity? We define a ground as a convenient reference level and just say the ground is potential energy 0. And then h is just your height above, or actually below ground would work as well. And so if h is 0, you get a potential energy of 0. And so again, you could consider an object at a height h and consider this path and say like let's say this is a to b, and then ub minus ua is equal to mgh. So let's do that. Say we start at a. And so what we get from our formula is ub minus ua equals mgh, minus 0. And we just pick this reference level where the ground is just a very convenient reference level. And that's a little more difficult to do in this case, though, because electrostatic forces, we can't pick a radius that's going to set one of these terms equal to 0, at least not any finite place where the potential energy would be 0, or where one of these terms would be 0. So what we do is, let's say, we start at A and end up at B. We can set a reference level to be, let's say point A was infinitely far away. Now, of course, by infinite, we just mean, let's say point A is far enough away that the interaction between Q1 and Q2 is going to be completely insignificant at that distance, or just however far we need to go. And so if we set RA equals infinity, let's plug this in. Let me write that here. Let's say that RA equals infinity. Then we have UB minus, and let's say that the potential energy at A is then 0. Because there shouldn't be any interaction if the particles are infinitely far apart. So yeah, it'd be a good place to set the potential energy at A equal to 0. So we'd have UB minus 0 would be KE Q1 Q2 over RB minus, if RA is infinite, this term is 0. And B is some arbitrary point that's a distance r away from Q1. So just like we have a reference level for gravity near the surface of the Earth, for electrostatic fields, we set our reference level to be infinitely far away, and then the potential energy is just a function of radius. So yeah, just UB, that's a potential at some distance r. That'd be KE Q1 Q2 over r. So that is our potential energy function for electrostatic fields. And again, let's see, that was about 39 minutes just to get to that result, which was, not that complicated of a calculation the way we wound up eventually doing it. But this idea that the force is conservative is very important, so I wanted to spend some time talking about that. Now, there's more to say about electric fields, but I want to break it up into smaller pieces. So I think I'll stop this video here. But next I want to talk about a little more about potential energy. Like here we have two charges. I want to talk a little bit more about potential energy, but we'll do that in a separate video.